Okay, so back to the variance, right? So I hope everybody's there. 35 students now. Some of them wrote. Okay, fine. So yes, the variance covariance matrix. This is what you have to know. We can write it in matrix form as 1 over n minus 1 x transpose x minus n x bar transpose. So S can also be represented as, here's another form. Actually, we are going to use this one more, right? I'm asking to prove. Can you try? So S can also be represented, S can also be represented as 1 over n part is there, x transpose x, right? You can see you have x transpose hx, where h is this thing. Can you try proving that? So S equals, we already showed 1 over n minus 1 x transpose x minus n x bar transpose. Right. So here it says we can again write it as n minus 1 x transpose, sorry, I minus 1 over n 1 transpose x. So this part we know denote by h. Can you show? Nothing much, just plug in for x bar, right? We know x bar in matrix form. So x transpose x, that's our data matrix, minus n x bar transpose. You simply have to plug in the matrix notation. So earlier we showed that x bar equals 1 over n x transpose 1. That's x bar. X bar transpose is transpose of that one. So 1 over n x transpose 1 transpose, it comes as 1 transpose x transpose back to x. Those are the properties of the transpose and all, right? I hope you remember that. So what I just said is x transpose 1 transpose equals 1 transpose x transpose is x. So that equals 1 over n minus 1 x transpose x. Be careful with the underlines, that means the vectors and matrices, right? So you can see 1 n cancel off here. So you have 1 over n part. You have x transpose 1 transpose x. Now you can take x transpose x out, but you can see in the second term you have something in the middle. So you have to take x transpose from left side and X from the right side. Remember matrix properties. We learned the matrix algebra first because of that. So you have to take X transpose from this side, X from the other side. From the first term, what's left here? You take X transpose out. You take X transpose out, X also out. So what's the remaining part there? Whatever you have to write here, if you multiply that by X transpose and X from right and left sides, you end up with just X transpose X. So here it would be, you can hear me, right? Yes. Thank you. Yes, okay. Yeah. Yes, Shashika, that's correct. Tarushi, yes, Tarushi. Is that a new name? I don't know. But anyway, it should be I, right? We cannot say H directly. So from this side, from this part, we have I. From this part, we took X transpose and X out. So we end up with 1 over N, 1 transpose, right? That's actually our H. So that's why it says we can show this in this form also, X transpose HX. Actually, that's the form we mostly use because that's the correct matrix form. Because X bar is a vector, but we have the data matrix, right, originally. So it's better to write it in data matrix form. So finally you end up with S equals 1 over N minus 1 X transpose HX. Any question there? Darwani, if the things are not clear, the dimensions, everything, please spend some time, right, after the class on these things, because this is the beginning of the semester and I hope you are done with the exams and all. And at the beginning, it's always good to catch up with those things because looking at the dimensions, you can always check whether what you are doing is correct or not, at least up to some extent, right? So try to spend those like 10 notional hours per week for a 3 credit course, right? 3 here, so you have 7 remaining. So try to spend some time on this subject. Because later on you will not have that much of time because you may have assignments from different subjects likewise, right? Not going to be that easy. So at this time, it's good to spend some time. Okay, so that's the variance covariance matrix. Now, numerical measures we learned sample mean vector and variance covariance matrix. Okay, now what are we doing actually? You have to always remember that, right? We are still summarizing data. So mean and variance, those are summary measures, right? So remember, we are trying to summarize our data. Now, read this, please. The sample covariance matrix summarizes the information about the dispersion of the data. Yeah, that's what we are trying to do, right? We try to summarize the dispersion of our data set, right? Our data matrix. However, there's a blank space here. possible distinct elements in S to examine. So I'm asking now, how many distinct values in S? So you know S is a P by P matrix. You have S11 up to SPP along the diagonal. 1, 2 up to 1P here. 2, 1 up to 2P here. 1, 1, 2, 1 up to P1. Sorry. So altogether there are P times P elements. I'm asking how many distinct elements? Because I already mentioned that it's a symmetric matrix, right? Because covariances are the same. S12 is same as S21. 1P same as P1. So how many distinct possible values in this P by P matrix? That's the information that comes to the blank space. Oshan, no, not really. Times, no. No, Pavanti, it's also not correct. In a P by P matrix, how many distinct values? A P by P symmetric matrix, how many distinct values? No, Shashika, n doesn't matter. We don't care what n is because n doesn't matter here. P by P matrix we have. No, Ishan, that's also no. Osha, the part is correct. So definitely, okay, I'll make it easier. Sure. I'm getting complicated answers. P square plus P over 2. How come P square plus P? No, that's not also. Okay, I'll make it easier. So definitely the diagonal elements are distinct, right? There may be situations that some of them are equal, but usually diagonal elements, we have P of them. So definitely P plus. How many of diagonal elements? Dishan, P plus 1. Some of the answers I have to simplify actually. Yes, Tarushi, that's correct. Chatunia, that's also correct. So I already said P plus something. No, Himasha, not Tasni. That's also not correct. Probably this P square plus P over 2. No, plus. That's also not. Okay, so diagonal, yeah, I just got one correct answer, I guess. No. How come this P plus 1? I don't understand. Okay, anyway, P. P is the number of diagonal elements, right? Off diagonal, how many off diagonal elements? That's the question. You have Altogether, P responses, taking 2 at a time, how many possible values? That's it, right? Off-diagonal elements are the covariances. So how many covariance terms? You have P responses, taking 2 at a time, how many combinations? So how do we write it? P plus PC2, right? Yeah. So PC2 is P minus 1 over 2. Some of you had this answer. So altogether P plus PC2, that's the number of possible distinct values. Is that clear? If not, you can ask, I can explain again. P plus PC2. Diagonal elements, that's P. Off diagonal elements, PC2. P choose 2. So P plus PP minus 1 over 2. That would be the possible distinct elements in S to examine. Any questions there about the number? Yeah, Hanshan, you have given the answer finally. Yes, that's also correct. I had one correct answer before also. Any question with that value? Okay, that's there. Now you have a P by P matrix, right? Yeah, this is the P by P matrix you have. So you have to find, or I ask you to find the number of distinct values here, right? Definitely you have P of them along the diagonal. These are the variance terms. Independently we calculate for each response separately, right? So there are P such values along the diagonal. So that's why I wrote P plus. Then I need the number of off-diagonal elements, right? Off-diagonal elements means this part. Because that equals to the lower triangle also. So I just need the upper triangle, those values. So I have 1, 2 up to 1P, right? Then 2, 3 up to 2P. Likewise, you have all the off-diagonal elements. So off-diagonal elements, there are P responses. There are P responses. So taking 2 at a time, how many pairwise covariance terms? That's PC2, right? Because like it's 1 versus 2, 1 versus 3, 1 versus 4, up to 1 versus 5. Then 2 versus 3, 2 versus 4, 2 versus 3, likewise. Then 3 versus, likewise. Number of pairwise different values would be PC2. So if we look at a smaller one, we'll say 3 by 3 case. So you have S11, 12, 13. Right. So 3, that's a diagonal, plus you have 3 responses, taking 2 at a time. How many possible combinations? Right. So altogether there are 6. So 3C2 is 3. That's these 3. And this 3 is diagonal elements. Right? Is that clear, Oshan? It's simplified to P times P plus 1 over 2. Maybe, I don't know. P plus. Sometimes some of your answers I have to simplify and see. Maybe you are correct. Yeah, probably you gave that answer earlier. We can check, right? P plus P minus 1 over 2. That's what we had. Then P square minus P plus 2P over 2. Yeah, it's p square minus p over 2. හරිද මං කරනවා? Plus p, right? So pp plus 1 over 2. Ah, yes, that's correct, Roshan. Yeah, that simplifies to pp plus p square plus p over 2. So finally pp plus 1 over 2. I thought it has a triangle values 1 plus 2 plus up to p. Okay, finally probably that comes to that. Yeah, so yes, when we count the numbers, there are different ways. Yeah, sorry if I said your answers are wrong. And when you gave it as pp plus 1 over 2, right? That answer is also correct. Because this simplifies to that. So simply saying it's p plus pc2, right? That's the number of distinct elements in the matrix. Is that clear now, Dasita?
Yes, madam.
Okay, thanks. Okay, so that's the number of distinct elements. Now, again, I'm saying we are trying to summarize our data, right? Now, this says possible distinct elements in S to examine and may not provide a good summary measure when P is large, right? So here we have a summary measure. When we have a univariate data, spread measure is just a single value, right? But if your P is large, the number of distinct elements would be much higher. As an example, suppose we have like 5 responses. If we have 5 responses, how many distinct elements in S? When P equals 5, what's the number? P plus PC2. Yes, 15, right? Yes, Hashini. Then it's going to be 15. And suppose P equals 10, what would be the number? 10 plus 10C2. 10 times 9 over 2, 45, 10, 55, right? Yes, yes, Pavanti, yes, Ashoka, it's 55. Yes, Kasuni. So it's going to be 55. So you can see when P is large, we have large number of summary values. So even a small p, you can see when p equals 5 also, we have 15 different measures in our variance covariance matrix, right? So it's not going to be a good summary measure, especially when for larger number of responses. If p equals 10, there would be 55 distinct elements in your summary measure. So think about it. In univariate cases, 55 would be the number of observations you have, right? So we always try to summarize to get a better idea of the data, right? If we have a large number as summary measures, then it's not going to help us that much, right? So that's what this explains. So may not provide a good summary measure when P is large. So two other summary measures that have been derived from S are the total variance. So the matrix S, using that one, we define two other summary measures. One we call the total variance, which is simply the sum of the sample variances of the P responses, right? Sum of the sample variances of the P responses, that means whatever you have along the diagonal, right? Sum of the variances means the sum of the diagonal elements. That means simply the trace of S, right? So we have two other summary measures defined. One is the total variance. Total variance is the trace of S, trace of the matrix S. And also another one we call the generalized variance. Generalized variance is the determinant of S. right? So when the number of responses is large, then there would be large number of distinct elements in our S matrix. So to further summarize our spread measure, we use two other um, measures derived from our S, the summary measure S, which are the trace of S and determinant of S. Trace of S we call the total variance. So total variance, it's there in the name, right? The off-diagonal elements are covariances. The variances are only along the diagonals. So trace of S is the total variance of the data. And generalized variance, it's a generalized value. We cannot directly explain that with the name. But anyway, that's the determinant of this matrix S, right? However, okay, there's a but everywhere. However, as the following example shows, there are instances in which these summary measures fail to detect important differences in the correlation structure. So remember one thing, we are interested about the correlation structure of the multivariate data, right? Correlation structure, covariance structure, kind of similar thing, not similar, sorry. Covariance and correlation, not similar, but we can compute one from the other, right? So covariances, covariance structure, correlation structure of the data is also important, because if there are no significant correlations between our responses, why bother with these multivariate techniques, right? We can separately analyze the responses using univariate methods. So correlation structure of the data is an important thing in multivariate data. Okay, so this example says, however, these summary measures may not work all the time, right? Here's an example for you to work on. Consider the following sample covariance matrices. So these are just bivariate cases. You have 2 by 2 matrices, right? S1 is the first variance covariance matrix. S2 is given, S3 is given. So I'm asking you to find the correlation coefficient, the determinant of the matrix, and the trace of the matrix, right? That means correlation, bivariate cases. So correlation between the two responses, total variance and generalized variance. Okay, first matrix. What are the three values? You can calculate and see. Now you should know how to calculate the correlation. What's the equation to calculate correlation? Give me a second, please.